In week 4, we're going to take the math we learned in week 1 and the expanded definition of what a variable can store in week 3, and we're going to combine them together, where we're going to figure out what happens when we do a plus b, or a minus b, or a times b, when a and b store more than just a scalar value. So I'm going to step through the PDF. I might jump around a little bit, but we will cover it all. So first things first, equal matrices. Two matrices are equal if they have the same elements and the same size. So this size thing is going to be really important, where we define it as the rows times columns of a matrix. So if two matrices are equal, they need to have the same rows, same columns, and the same elements, the same value in each corresponding location. Okay. Number 2, array operations. So matrix operations follow the normal rules of linear algebra. Array operations can be performed element by element. So MATLAB has these two things that come into play whenever we're doing math: linear algebra versus element by element operations. Element by element operations are probably more intuitive for students. And here's our MATLAB syntax for element by element operations. Note, element by element operations can only be performed if matrices are the same size. Meaning you have the same number of rows and the same number of columns. Okay, but if I want to add two matrices together, I'm just going to take all the elements in matrix A and add them to the corresponding element in matrix B. So if I have a matrix A, B, C, D plus E, F, G, H, I can go ahead and say, okay, it's A plus E, these two elements, B plus F, these two elements, C plus G, these two elements, and D plus H. Where element by element means that my final result is going to be the same size, where each element in each matrix is added or multiplied or divided or subtracted by the corresponding element in the other matrix. So if I want to do that in MATLAB, here's my syntax over here. Note, addition and subtraction, no modification. It's just plus and minus. However, when we get to multiplication, division, and exponentiation, we have this additional dot operator that we need to use, because the default math in MATLAB is not element by element. Okay? So we need to add this dot in front of the asterisk, in front of the division sign, and in front of the exponentiation if we want to perform this element by element. And it's really useful to do this when, for example, we're calculating the value of a mathematical function across many values. So if I have a polynomial y equals x squared plus 5x plus 3, I can easily do that using these element by element operations if x is a vector. So let's say x is the values from -5 to positive 5. I can just say y equals x dot caret 2 plus 5 dot asterisk x plus 3, where this dot in front of those means it's going to do it element by element. Take the first value in x, do the calculation. Second value in x, do the calculation, etc. One other thing to note, built-in MATLAB functions like sine and cosine, nth root, square root, all those fun things are performed element by element. So that's the more intuitive piece for students. The challenging piece for this week, and for a lot of it, is the linear algebra piece, where the default math in MATLAB is linear algebra. So let's go ahead and talk about how linear algebra handles these 5 different operations, how linear algebra defines addition, subtraction, multiplication, division, and exponentiation. So first, addition and subtraction. Turns out addition and subtraction automatically is performed element by element. So between array operations and matrix operations, it's the same thing. We also have scalar addition, where if I say A plus 5, it's going to take 5 and add it to each element in A. Properties, doesn't matter if I do it out of order, A plus B, B plus A, it'll be the same thing. Doesn't matter if I do B plus C first or A plus B first, same thing. So here is our definition of linear algebra. So if I do A plus B, here's my MATLAB syntax. A minus B, MATLAB syntax. And here's how I define element by element operations, where the I is the row I'm in. So the row I and the column J, where I'm saying all the elements in A add them to the corresponding element in B. So if I do scalar addition, scalar subtraction, what this means down here is that all the elements in A add k to it. That's what that means. Okay, but that's how we define linear algebra, addition, subtraction, and our MATLAB syntax. Next one, matrix multiplication. How does MATLAB or linear algebra define multiplication between two matrices, A times B? So first things first, if that A is a scalar, so if I have 5 times A, it just multiplies all the elements by that scalar, not complicated. Before we get to actual matrix multiplication, we need to stop and pause and talk about the dot product. The dot product is super important when it comes to matrix multiplication because matrix multiplication is a bunch of dot products. So here's some properties. You guys can look at that. We'll skip over it. The dot product. The dot product of two vectors. So note, dot product is between two vectors. By definition, dot product vectors. Vectors meaning they're either rows or columns does not matter. The dot product of two vectors is a scalar and can only be performed between two vectors of the same length. So once again, it doesn't matter if it's rows or columns as long as they have the same number of values. So if I have a vector A, B, C, D dot W, X, Y, Z. So it doesn't matter if these are rows or columns, they have the same number of values. The dot product is this equation here. It's the sum of all of my elements multiplied by each other. So it's A times W plus B times X plus C times Y plus D times Z. This times this plus this times this plus this times this plus this times this. It's element-wise multiplication and then add all the numbers together. That is the dot product. In MATLAB, if we want to perform the dot product, we can use the dot function. So here is my MATLAB syntax in order to perform the dot product. So we need to know the dot product because matrix multiplication is just a whole bunch of dot products. Keep that in mind. Okay, so let's go ahead and figure out how to do matrix multiplication. So this here on down starts defining what matrix multiplication is. So if A and B are two matrices, the operation A times B can be carried out if and only if the number of columns in A is equal to the number of rows in B. Okay, so this tells us that we can only perform matrix multiplication sometimes. It depends on our two matrices. Specifically, it depends on the size of our two matrices. So if the number of columns in A is equal to the number of rows in B, then the result is a matrix that has the same number of rows in A and the same number of columns as B. So I like to use this picture here. If I take A times B to produce C, if A is an M by N matrix and B is an N by P matrix, then C is going to be an M by P. So note, we've got these inner dimensions here. Check to see if they're equal to each other. They are. So my result means that C is going to have the same number of rows as A, and C is going to have the same number of columns as B. So before we do matrix multiplication, we need to do this check to make sure that our matrices are of the proper size. So note, they're not the same size. They're not the same size. They have the same number of columns and rows. Columns in A, rows in B. So if that's true, if this matches, these inner dimensions match, then my product is the dot product between the rows in A and the columns in B. So once again, matrix multiplication is just a dot product between rows in A and columns in B. So here we go. So here's essentially what we get. If I do A times B, then I'm going to take the dot product between row 1 in A and column 1 in B. So that's my first answer. C of 1, 1 is a dot product between the first row in A and the first column in B. Then, right here, my second, right here, take the second row in A and the first column in B, perform the dot product. And we literally go through and perform all the combinations of dot products between the rows in A and the columns in B. We'll go over lots of examples in class, but that's what we're doing. Matrix multiplication is just the dot product between rows in our first matrix and columns in our second matrix. So we need to check to make sure the number of elements in our rows in our first matrix matches the number of elements in our columns. Okay. That's why we need to check to see if the sizes match. Here's some properties. I want to point out a couple things in these properties. So the order in which you do the multiplication doesn't really matter. So you can do BC first or AB first. It doesn't matter. But A has to be next to B next to C. You can do BC first, but A needs to stay over here on this side. Same thing. You can do AB first, but C needs to stay over here. If we have a scalar, same here. So we can do B plus C first, and we can distribute A. But note, A is over here on the left side, which means it's over here on the left side and over here on the left side when we distribute. Same thing here. A is on the right side, so it stays on the right side when we distribute. And the reason for that is because order matters. A times B is not equal to B times A. This order of multiplication doesn't matter. This multiplication versus this one first, that doesn't matter, but they need to stay in the right order. They need to be A times B, which is not equal to B times A. So make sure you keep that in mind. When it comes to powers, so we're not really going to talk about exponentiation with matrices because exponentiation is just multiplication. So we just rewrite it as a multiplication, and we just check to see, okay, do the sizes match? Does the number of columns in A match the number of rows in B? Then we can do our multiplication, or our exponentiation. And it turns out this will only work with square matrices. Okay, that's multiplication. Division. Division turns out with matrices is not defined. Instead, division is also matrix multiplication. It's also multiplication, where we calculate the inverse of a matrix. And it turns out this can only be performed with square matrices. It's kind of like saying 5 divided by 3. I want to divide two values. It's the same thing as saying 5 times 1/3. This is what we're going to do when it comes to matrices. It's the scalar 5 divided by the inverse of 3. That's what we're doing with matrices. There's two different types of division defined by MATLAB. We have right division and left division, and it really just depends on where the inverse shows up. So right division, if I do A divided by B, that's going to be A times B inverse. If I do A left divide B, it's going to be A inverse times B. So it points to whichever one is inverted. Okay, here's my MATLAB syntax. Okay, we will see this syntax a lot later on in the class when we're solving systems of equations. Okay, so how do we do division? We don't. We do multiplication. We do multiplication with the inverse. So how do we find the inverse? A couple notation vocabulary. The identity matrix is the matrix equivalent of 1. It's the matrix equivalent of 1. The symbol for it is I. And we can create the identity matrix using the I function. That's why we talked about it. The inverse matrix is a square matrix, so we're dealing with square matrices, such that A inverse times A equals A times A inverse equals I. Kind of like saying 5 times its inverse equals 1. Same idea. And only square matrices have inverses. So that means not every square matrix has an inverse either. So square matrix, but not every square matrix. In order to figure out if a matrix has an inverse, we need to calculate the determinant. We will talk about how to calculate determinants for 2x2 matrices. Right now, we will get to bigger determinants later on in the class. If you want to calculate a determinant using MATLAB, you could use the DET function or the determinant function. So we calculate a determinant. If the inverse exists, that means its determinant is not equal to 0. And we call that matrix non-singular or invertible. You'll see singular in errors all the time in MATLAB. So it's important you know what non-singular means and what singular means. So if the inverse does not exist, that means its determinant is equal 0. It's considered singular and non-invertible. So we either have determinant of a matrix equals 0, it's singular, non-invertible, inverse doesn't exist. Or it's not equal to 0, it's non-singular, it's invertible, its inverse does exist. If its inverse exists, you can use the I and V function in MATLAB to figure it out. And here's some properties. If you have to calculate it by hand, here's our equation. A inverse equals 1 over the determinant of A. This notation here is determinant. You might think, oh, that's absolute value. It's not. If you have this matrix, then it's determinant. Okay, so it means determinant. So 1 over the determinant of our matrix times A adjoint. So here's our steps. First, calculate determinant. Then check to see, is your determinant equal to 0? If it is, then go ahead and stop. If it's not equal to 0, keep moving forward. If the matrix is invertible, find the adjoint or adjugate. You'll hear both of those terms to find the adjoint matrix. And then plug the result into the formula. We will focus on 2x2s right now. Here's our steps for a 2x2, and you'll just have to memorize these. So for a 2x2 matrix, we've got this matrix here, A, B, C, D. Our determinant is these values minus these values. I call it a fish method. I like to draw my little fish, where it's A times D minus C times B. That's how we calculate determinant. If we want to find the adjoint matrix, then these two switch places. So D and A switch places, and then these two have their sign negated. So B becomes negative and C becomes negative. That's how we find the adjoint matrix. So then when you put it all together, this becomes our final formula for the inverse of a 2x2 matrix. Once we have that, then we can use that in our division. So we can say A inverse times B, where A inverse is figured out that way. Okay, so division is really just multiplication, more multiplication, okay, which is some additional steps. Okay, last thing to talk about for this week is, why do we even care? Why do we even want to do this? And the reason for that, at least in this class, linear algebra is awesome. It's used in lots of different fields. But the main application for our class is because linear algebra rules for array multiplication, for matrix multiplication, provide a really convenient way for writing and solving systems of equations. And we'll look at these a lot once we get past the midterm. But really, that's our main application for this class, is solving systems of linear equations. And it turns out a system of linear equations can be written in matrix form, which means we can solve them using linear algebra notation. So here's two different ways to write a system of equations in matrix form. We're going to skip over column format because it's less, they're literally the same. But column format isn't used as often as row format. So here's a system of equations. You might also see it, might be more familiar with it like this. Hopefully you've seen system of equations before. You should have learned it in math. But if we have a system of equations, we can write it in matrix form, where we have three matrices that form. We have an A matrix that's filled with our coefficients, the values in front of our unknowns. We have our X vector, which is our vector of unknowns. This is literally full of letters. And B, those are our constants from the right-hand side. So all the constants exist on the right-hand side. So here's how we can write it in matrix form. AX equals B. And note, if we want to solve for X, then we just take B divided by A, right? Almost. This is matrix algebra, so we can't divide, but we can multiply by an inverse. So if I take A inverse and multiply it on both sides, note, multiplying it on the left side, so I'm multiplying on the left side here. So A inverse times A is identity. So X equals A inverse times B. This becomes my solution. So I've boiled my solution down to one basic matrix multiplication once I find the inverse. That's really what it comes down to. So if I look at this system, I've got matrix A, which is going to be filled with my coefficients. So from equation 1, it's 3, 5, negative 2. From equation 2, it's 4, 1, 1. From equation 3, it's -4, -4, 5. Where here's the value in front of x, in front of y, in front of z. So notice we have this little grid that forms. Equation 1, 2, 3, value in front of x, y, z. Then I have my x vector, which is full of my unknowns, x, y, z, in this order. And then my b vector, that's filled with my constants on my right-hand side. So -8, 8, 10. So I can solve for this x vector here, x, y, z, equals the inverse of this matrix times this vector. There we go. Solving my system with one basic matrix multiplication, which can be easily done in MATLAB, where if we set up this matrix in MATLAB, set up this vector in MATLAB, then our solution becomes as simple as x equals a left divide b. Okay, so I did skip over that a little bit, where there are two different kinds of division. Oh no, I talked about it. In two different kinds of division. This left division really shows up in solving systems of equations. Other than that, you can ignore it. But left division shows up in solving systems of equations. Okay. And this is why. A left divide B. Okay, so the last thing in this material, I have this flow sheet that steps through how to make a decision about what kind of operation to use. So are you doing math in MATLAB? Yes or no? What type of data do you have? Do you have scalars? Proceed like we've done previously. If you have arrays, vectors, or matrices, then ask what kind of math. Do you want element-wise, or do you want to do linear algebra? If you want to do element-wise, ask yourself, what's the size of the matrix? Are they different sizes? Can't do it. Are they the same size? Then what kind of operation are you trying to use? For addition and subtraction, you're fine. Go ahead. For multiplication, division, exponentiation, add that little dot operator, that little dot in front. If you're trying to do linear algebra, then ask yourself, okay, what kind of operation? Are you trying to add matrices, subtract matrices, multiply, exponentiation, division? If you're adding matrices, check your size. If they're the same size, you're good to go. If they're different size, not allowed. If you're trying to do matrix multiplication, you have A, which is, let's say, an M by N matrix, and B is an R by C matrix. Check to see if these inner dimensions match. If they match, you're good to go. And then you can perform the dot product between the rows in A and the columns in B, and this is how I defined it for each value. If you're trying to do exponentiation, check the size of your arrays. If it's a square matrix, rewrite it as matrix multiplication and jump up to here. If it's not square, you can't do it. Division, if you have A, right divide B, rewrite it as multiplication. Check to see the size of B. No, B needs to be square in order to have an inverse. Calculate the determinant. If it's 0, inverse doesn't exist. If it's not 0, calculate the inverse and then go ahead and do matrix multiplication. If you are doing left division, then ask yourself, are you solving a system of equations? If you are, rewrite it as B inverse times A. Go back up and calculate the inverse. If you're not, why are you thinking of left division? And then still rewrite it as B inverse times A and go back up. Find the inverse and then do your matrix multiplication. So there's our big flow sheet of how we're going to go about making decisions about what kind of math we are going to do in MATLAB.